Myself, Dr. E. Helena, working as an assistant professor in the Department of Mathematics, Fatima College. I am happy to share my lecture on the topic, the basic theorems of bounded linear operators. In this lecture, let me introduce open mapping and prove open mapping theorem with the help of two lemmas. The definition of open mapping goes like this. A continuous linear transformation T of a normed linear space n into a normed linear space n dash is said to be open if for every open set G in n, its image T of G is open in n dash. Open mapping theorem statement is if B and B dash are Banach spaces and if T is continuous linear transformation of B onto B dash, then T is an open mapping. That is, we are considering two Banach spaces B and B dash and T is a continuous linear transformation from B onto B dash. What we have to prove is for every open set G in B, its image T of G is open in B dash. So for that, let us prove two lemma. First lemma, let us consider open spheres centered at x and radius r denoted by S of x comma r and a open sphere with center at the origin and radius r as SR. What we have to prove here is S of x comma r is equal to x plus SR and SR is equal to r into S1. So to prove S of x comma r is equal to x plus SR, we have to prove both the containments. Let us first prove the first containment, namely S of x comma r is a subset of x plus SR. For that, let us take a point y in S of x comma r. By the definition of open sphere, norm y minus x is less than r. If I take y minus x is equal to z, then we have norm z less than r. By the definition, we know this z belongs to SR. Since y minus x is equal to z, y is equal to x plus z. As z belongs to SR, we have y belongs to x plus SR. Starting from y in S of x comma r, we have proved y in x plus SR. Therefore, S of x comma r is a subset of x plus SR. Also, by the definition of the open sphere, it is obvious that x plus SR is a subset of S of x comma r. Hence, we have S of x comma r is equal to x plus SR. Next, we have to prove SR is equal to r into S1. For that, let us consider SR. SR is equal to set of all x such that norm x less than r. That is by the definition of a open sphere. This can be written as set of all x such that norm x by r less than 1. If we take norm x by r is equal to y, then SR can be written as ry such that norm y less than 1. Norm y less than 1 implies y belongs to S1. Therefore, SR can be written as r into S1. Thus, we have proved SR is equal to r into S1. Second lemma, if B and B dash are the Banach spaces and if T is a continuous linear transformation of B onto B dash, then the image of each open sphere centered at the origin in B contains an open sphere centered at origin in B dash. That is, if you are considering two Banach spaces B as well as B dash, then the open sphere SR in B and SR dash in B dash, the image of SR contains the sphere SR dash. So we are giving the notation SR and SR dash as open spheres centered at the origin and radius R in B and B dash. By lemma 1, we have SR is equal to R into S1. Therefore, T of SR is equal to T of R into S1. As T is linear, this can be written as R into T of S1. To prove lemma 2, it is enough to prove that T of S1 contains some open sphere SR dash so that T of S1 is open. We can prove this theorem in 4 stages. Stage 1, let us prove an interior point y0 of T of Sn0 closure lies in T of Sn0. So let us take x in B. So by the definition of SR, SR is a open sphere centered at the origin and radius r in B. Therefore, for some positive real number, x belongs to SR. If we choose sufficiently large positive integer n, then this x belongs to Sn. So x belongs to B implies x belongs to Sn. That is, B is a subset of union n from 1 to infinity Sn. As for some n, x belongs to Sn. Also, by the definition, it is obvious that union n from 1 to infinity Sn is a subset of B. Therefore, we have B is equal to union Sn. As T is on 2, we have B dash is equal to T of B. But B is equal to union Sn. Therefore, B dash is equal to T of B is equal to T of union Sn. As T is linear, it can be written as union T of Sn. Since B dash is complete, that is the Banach space is complete, it is of second category. Hence, by Bayes category theorem, the closure of at least one set in the sequence T of Sn must have non-empty interior. That is, by Bayes category theorem, one element in the sequence T of Sn has its closure must have non-empty interior. So, let us take for some n naught, interior T of Sn naught closure is not equal to empty set. Let y be a interior point. Since it is non-empty, let us take y to be the interior point of T of Sn naught closure. Therefore, there exists a open set G such that y belongs to G subset of T of Sn naught closure. That is, as y is an interior point, by the definition of interior point, there exists a open set G which contains y and is contained entirely inside the set T of Sn naught closure. Therefore, y belongs to T of Sn naught closure. We know that A closure is equal to A union D of A. That is, D of A is the limit points of A. So, A closure is A union D of A. As y belongs to T of Sn naught closure, y is a limit point of T of Sn naught or a point of T of Sn naught. If it is a limit point of T of Sn naught, then the neighborhood of y contains another at least one point y naught, such that the neighborhood G of y contains a point y naught of T of Sn naught. Hence, y naught is such that y naught belongs to G subset of T of Sn naught closure. Therefore, y naught becomes an interior point of T of Sn naught closure. Thus, we have the interior point y naught of T of Sn naught closure to be a point in T of Sn naught itself. Now, stage 2, to prove 0 is an interior point of T of Sn naught closure minus y naught. So, let us now consider a mapping f from B dash to B dash given by f of y is equal to y minus y naught. This mapping is a homeomorphism. We know by the definition of f, it is clear that it is 1, 1 and on 2. So, let us now consider yn to be a point in B dash such that yn converges to y in B dash. As B dash is complete, this is possible. So, let us now consider f of yn. By the definition of f, it is yn minus y naught. As yn converges to y, yn minus y naught converges to y minus y naught, which by definition is equal to f of y. That is, f of yn is equal to f of y. And f inverse of y by definition equal to yn plus y naught. As yn converges to y, yn plus y naught converges to y plus y naught, which by definition equal to f inverse of y. Therefore, both f as well as f inverse are continuous, so that f becomes a homeomorphism. By stage 1, we have y naught to be an interior point of T of Sn naught closure. By the definition of interior point, there exists a open set G which contains the point y naught and contains entirely inside T of Sn naught closure. Therefore, we have f of y naught belongs to f of G subset of f of T of Sn naught closure. By definition of f of y naught, it is equal to y naught minus y naught, which is equal to 0. Therefore, we have 0 belongs to f of G, which is a subset of f of T of Sn naught closure. By the definition of f, this is nothing but T of Sn naught closure minus y naught. Since f is a homeomorphism, f of G is open in B dash. Thus, 0 is an interior point of T of Sn naught closure minus y naught. Stage 3, here we will prove T of Sn naught closure minus y naught is equal to T of Sn naught minus y naught the whole closure, which is a subset of 2n naught into T of S1 closure and S epsilon dash subset of T of S1 closure for some epsilon greater than 0. So first let us prove T of Sn naught minus y naught subset of T of S2n naught. For that let us take up element y in T of Sn naught minus y naught. Now, therefore, there exists a x in Sn naught such that y is equal to T of x minus y naught. By stage 1, we know y naught is a point in T of Sn naught. Therefore, again for some x naught belongs to Sn naught, y naught is equal to T of xn naught. Thus, we have y is equal to T of x minus T of xn naught. As we know, this T of xn naught is equal to y naught, which is equal to T of x minus x naught, as T is linear, where x and x naught belongs to Sn naught. Since x and x naught belongs to Sn naught, we have norm x less than or equal to n naught and norm xn naught less than or equal to n naught. Now let us consider norm x minus x naught, which is less than norm x plus norm x naught. As norm x and norm x naught less than n naught, this becomes 2n naught. That is x minus x naught belongs to S2n naught. That is T of x minus x naught belongs to T of S2n naught. So T of x minus x naught is y, therefore y belongs to T of S2n naught. As we have taken y in T of Sn naught minus y naught and we have proved y belongs to T of S2n naught, we have T of Sn naught minus y naught subset of T of S2n naught. By lemma 1, we know T of Sr is equal to R into T of S1. Therefore, T of S2n naught is equal to 2n naught into T of S1. We know if A is a subset of B, then A closure is a subset of B closure. As we have T of Sn naught minus y naught subset of 2n naught into T of S1, we have T of Sn naught minus y naught closure subset of 2n naught T of S1 the whole closure. Since f is a homeomorphism, we know f of A closure is equal to f of A the whole closure. As here f is homeomorphism, f of T of Sn naught closure is equal to f of T of Sn naught the whole closure. By the definition of f, we know f of y is equal to y minus y naught. Therefore, f of T of Sn naught closure can be written as T of Sn naught closure minus y naught, and f of T of Sn naught the whole closure can be written as T of Sn naught minus y naught the whole closure, and we have proved this to be a subset of 2n naught into T of S1 the whole closure. As we have the scalar multiple of the sphere T of S1, let us define a mapping G from B dash to B dash such that G of x is equal to 2n naught x. Here it is clear that G is 1 1 on 2 as well as bicontinuous for n naught not equal to 0. Therefore, G is a homeomorphism. As G is a homeomorphism, again we can have G of T of S1 the whole closure is equal to G of T of S1 closure. By the definition of G, we have 2n naught T of S1 the whole closure is equal to 2n naught T of S1 closure. Thus, we have T of Sn naught closure minus y naught subset of 2n naught T of S1 the whole closure as 2n naught into T of S1 closure. Since 0 is an interior point of T of Sn naught closure, we have 0 is an interior point of T of S1 closure. 0 is an interior point of T of S1 closure gives, given epsilon greater than 0, we have a open sphere S epsilon dash such that S epsilon dash is a subset of T of S1 closure. Stage 4. Now we prove S epsilon dash is a subset of T of S3. In stage 3, we have proved S epsilon dash is a subset of T of S1 closure. Now we will prove S epsilon dash is a subset of T of S3. For that, let us take Y element in S epsilon dash. By the definition of open sphere, norm y is less than epsilon. As we know in stage 3, S epsilon dash is a subset of T of S1 closure and y belongs to S epsilon dash. We have y belongs to T of S1 closure. As y belongs to T of S1 closure, there exists a vector y1 in T of S1 such that norm y minus y1 is less than epsilon by 2, and y1 belongs to T of S1 gives y1 is equal to T of x1. For some x1 belongs to S1, so that norm x1 is less than 1. As in stage 3, we have S epsilon by 2 dash subset of T of S1 by 2 closure. Since norm y minus y1 is less than epsilon by 2, we have y minus y1 belongs to s epsilon by 2 dash, and we know which is to be a subset of T of s1 by 2 closure. Therefore, there exists a vector y2 in T of s1 by 2 such that norm y minus y1 minus y2 less than epsilon by 4 and y2 is equal to T of x2 and norm x2 less than 1 by 2. Continuing in this manner, we get a sequence xn in B with norm xn less than 1 by 2 power n minus 1 and norm y minus y1 plus y2 plus and so on yn less than epsilon by 2 power n, where yn is equal to T of xn. Let us take Sn to be x1 plus x2 plus and so on plus xn. Therefore, norm Sn by the definition of norm less than or equal to norm x1 plus norm x2 plus and so on norm xn. As we know, norm x1 is 1, norm x2 is less than 1 by 2 and so on. Norm xn is less than 1 by 2 power n minus 1. Norm Sn is less than 1 plus 1 by 2 plus and so on plus 1 by 2 power n minus 1, which is less than 2. Now for n greater than m, let us consider norm Sn minus Sm. We have Sn is equal to x1 plus and so on plus xn, and Sm is equal to x1 plus x2 plus and so on Sm. As n is greater, we have Sn minus Sm is equal to xm plus 1 plus xm plus 2 plus and so on plus xm. By the definition of norm less than or equal to norm xm plus 1 plus and so on plus norm xn, which is less than 1 by 2 power m plus 1 by 2 power m plus 1 plus and so on plus 1 by 2 power n minus 1. As it is a geometric series, on simplification, this is less than 1 by 2 power m minus 1 minus 1 by 2 power n minus m minus 1. As mn tends to infinity, this tends to 0. Therefore, we have Sn to be a Cauchy sequence in B. As B is complete, this Cauchy sequence converges to a point in B, that is x belongs to P. Since the norm is a continuous function, we have norm x is equal to norm limit Sn, which is equal to limit norm Sn, which is less than 2. As norm Sn is less than 2, this norm x is less than or equal to 2, which is less than 3. That is norm x less than 3 implies x belongs to S3. Now let us consider y1 plus y2 plus and so on yn. By definition, we have T of x1 plus T of x2 plus and so on T of xn. As T is linear, this can be written as T of x1 plus x2 plus and so on plus xn, which is equal to T of Sn, as Sn is equal to x1 to xn. Since T is continuous and as Sn converges to x, this implies T of Sn converges to T of x. Therefore, we have T of x is equal to limit T of Sn, which is equal to limit y1 plus y2 plus and so on plus yn, which is equal to y. Thus, we have y is equal to T of x, where norm x less than 3. So that we have y belongs to T of S3. So, taking y in S epsilon dash, we have proved y belongs to T of S3. Therefore, S epsilon dash is a subset of T of S3. That is, we have proved for a open sphere in B, the image contains a open sphere in B dash. Now, let us prove the theorem. Let T is a mapping from B to B dash. As T is a continuous linear transformation, we will prove T is open. To prove T is open, it is enough to prove that for every open set G in B, T of G is open in B dash. So, to prove T is open, we have to take a open set G in B and we have to prove T of G is open in B dash. Let us take Y to be a point in T of G. Therefore, for some x belongs to G, we have y is equal to T of x. As G is open, by the definition of open set, there exists a open sphere containing the point which lies entirely inside the set. Therefore, there exists a open sphere S of x comma r, that is x is an element in S of x comma r, which lies entirely inside G. By lemma 1, we have S of x comma r is equal to x plus SR, where SR is a open sphere in B centered at the origin. As S of x comma r is a subset of G, we have x plus SR is a subset of G. By lemma 2, there exists a open sphere S epsilon dash in B dash such that S epsilon dash is a subset of T of SR. Since S epsilon dash is a subset of T of SR, y plus S epsilon dash is a subset of y plus T of SR. We know y is equal to T of x. Therefore, we have T of x plus T of SR. As T is linear, we can rewrite this as T of x plus SR. That is, we have proved y plus S epsilon dash is a subset of T of x plus SR. Also, we know y plus S epsilon dash is equal to S dash y comma epsilon. Therefore, we have S dash y comma epsilon, a subset of T of x plus SR, which is a subset of T of G. Thus, we have shown that to each point y in T of G, there exists a open sphere in B dash centered at y and contained in T of G. Therefore, T of G is open. Thus, starting from G to be a open set in B, we have proved T of G is open. Thus, T becomes a open mapping. Thank you. In the next video, we will see some more theorems on bounded linear operators. Thank you for watching.